Regression models. Regression is one of the most important and commonly used statistics and machine learning techniques. Regression models generally refer to a class of machine learning techniques in which the goal is to predict a numeric outcome. The consensus is that there is a relationship between the target variable y, which is a numeric, and the independent variable x or a set of independent variable x. If we can figure this relationship out, then we can use this relationship to make prediction for the values of the target variable. However, regression models can also be used for classification purposes. Types of relationship. There can be different relationship between the dependent variable y and independent variable x or set of independent variable x. Here we're going to see an example of a linear relationship and k-linear relationship. Starting with the linear relationship. As you see in this picture, there is a linear relationship between x and y. We can estimate this relationship by this line. There is a positive correlation between x and y. As you see here, when we go from left to right, that means in the increasing direction of x, y also is going to increase. We can have a negative correlation between y and x, as you see here. On average, when we go from left to right in the increasing direction of x, y is going to decrease. There could be a nonlinear relationship between the independent variable and dependent variable. Here we're going to see examples of the curvilinear relationship. So as you see here, the relationship between y and x is not a straight line, but it's actually a curve. The relationship between an independent variable x and the dependent variable y can vary in quality of the relationship. It can be strong or it can be weak. Let's see an example of a strong relationship. So in these two pictures, you see a relationship between x and y that are strong. By that, we mean that these data points here are concentrated around the line that we estimate the relationship between. So the distance between these data points and the line that we estimated is small comparatively. So these we call this a strong relationship. When we use the linear regression to estimate this relationship and use it for prediction, we also presume that there's going to be a smaller a smaller error compared to a weaker relationship. So let's now see an example of a weak relationship. So as you see in this picture and the picture below this, this is still a linear relationship. The average, we can estimate it by this line here, but there is less concentration around the line and they are scattered. The data points are scattered. So there is more distance between the data points and the line. So we also presume here that if you use the linear regression model to make a prediction, presumably there's going to be a higher rate of error for our prediction compared to a stronger relationship. There could be no relationship between x and y. So when there is no relationship, we can't really figure that out because there is just none. So an example of this, as you see here in these two pictures. So for this picture, for example, there is no linear relationship or nonlinear relationship in a simple term between x and y. If we go on the left and right direction of x, meaning increasing x and y, we are not sure whether y would increase or decrease. So there is no simple answer to that. Similar to here, the data points are more concentrated compared to this case, but still if we go on the right side and left side of the x-axis, that meaning increasing and decreasing x, the y variable, it does change, but there is no trend into it. There is no pattern that we can recognize as a relationship. Correlation. You might remember the concept of correlation from statistics. Correlation is a normalized version of covariance that measures the relationship between two variables. So correlation measures the strengths of a linear relationship between two variables. The formula for correlation is as follows. So it's because it's a normalized or a standardized version of covariance, as you see here. That's why you see the covariance here, the covariance between x and y divided by the standard deviation of x and the standard deviation of y. The maximum possible value for correlation, if you remember, is 1. So when the correlation between x and y is 1, that's the maximum possible correlation. It shows the perfect relationship, linear relationship between x and y. The minimum possible correlation value is -1. And that shows a perfect negative relationship in the reverse direction. Of course, it's negative. And when the correlation between two variables is 0, that means there is no linear relationship between the two variables. Let's see some visual example for correlation. So this shows a high positive correlation, I would say perfect 1 correlation between x and y, because as you see here, there is absolute concentration of these data points around this line. This is a straight line. So this is a perfect linear relationship between x and y. And the correlation would be +1. This shows an example that there is no correlation between x and y. As you see here, data is scattered. They're not scattered around a line. You cannot see a pattern between the behavior of the spread of x and y here. So we would expect that the correlation between x and y would be either 0 or a small value. And this one shows a correlation between an example of correlation between x and y, which is negative and also -1. It's a perfect negative relationship because all data points fall on the a very perfect straight line here. So the magnitude of correlation is higher when the data points are close or concentrated around the line, as we see in the example A and example C. And when we have a spread out and dispersed data points, then the correlation it would be either 0 or a very small number. Coefficient of determination, or R squared. In statistics, R squares, or the coefficient of determination, is used to quantify as a measure to judge the quality of a regression model. When we have a single independent variable, especially if we don't have intercept, the R square, or the coefficient of determination, is equal to the square of R, which is the correlation coefficient. But they can be different for different models, however. So R square here is the coefficient of determination, and R is the correlation coefficient between x and y. Simple linear regression model. In a simple linear regression model, we only have one independent variable x that we want to use to make a prediction for the value of the dependent variable y. The idea in simple linear regression is to estimate the linear relationship between x and y using a formula of a line, a straight line. Every straight line, as you remember from algebra, has two components. One of them is the intercept, which is the value of y when x is 0. And the other one is the slope. A slope is the changes in y value over the changes in x value. How much you get for your y by changing in your x value. That's going to be the concept of the slope. So this is the formula of a linear regression model for the population. As we see here, we have beta 0 and beta 1 as parameters of the intercept and the slope. So this is the a straight line that we want to estimate this linear relationship. But as you see here, the real values of the data points are concentrated or scattered around this line here. So there is actually a distance or difference between this line and the estimation value. For example, for the independent variable value of xi, the linear regression model would say that, okay, this is my estimation of the variable. This is my estimation of the value of the y variable based on xi. But the real value of xi, yi for when x is equal to xi is actually yi here. So there is this difference. This is the error, the random error for this value that we have. So that's why we have it here. Then it comes to the question how we actually can find this line, or why this line, why not another line? There could be actually infinite number of lines that we can think it makes fit to this data set. But why this line? How can we find the linear regression formula for this? Ordinary least squares. So as we said, there could be an infinite number of lines can go through this data and appear to be fitting well, but how we can find the best line, which is the linear regression line. The idea here is to find a line that, equation of the line that has the least error on generally. If you look at this data, this line here, for example, for this data point xi, our prediction using this line is that this is the value that they're going to get, but the real value is here. So there is this error here, and you can see this error for other data points as well. So the idea of the ordinary least square is to minimize the sum of squares of error, and then based on that find the line that gives the minimum error generally. So the OLS method, the ordinary least squares method, finds the coefficients of the line, the intercept and the slope, such that the sum of the squares of errors given by the model through our data is minimized. This approach treats the data as a matrix and uses linear algebra operations to estimate the optimal values of the coefficient such that the error is minimized. Simple linear regression model. In simple linear regression model, there is only one independent variable. We can use the statistics to estimate the coefficients in the model using the OLS method. A sample is used to produce estimates for beta 0 and beta 1, or the coefficients of the linear regression line in the population. So using the sample, we can estimate this linear relationship equation for the sample and find the intercept B0 and the slope B1. And then based on this, we can induce a relationship for the population. So this is going to be our estimation of this line on the left, which is beta 0 as intercept and beta 1 as the slope, the linear regression model in the population. In practice, however, the simple linear regression is usually not that useful because most of the time there are more than one independent variable or predictors in the system.